share my screen. Okay. What happened? Okay, so let's get started. So let me give you a map of the rest of the semester. So you will do 2 more assignments in groups. Your last week of class where where your exams and all starts, I think on somewhere around 4th, 5th April. So we'll give you 1 assignment today, which is again 3 weeks, but I think we'll have to extend that given that the exam week will fall in the middle. So don't ask for too much extension because normally we give 2 weeks and then a 1 week extension. So this one will set the thing for 3 weeks. And then we understand there's an exam week in the middle. So maybe you can expect a 4 or 5 days extension at the end. And then another 2-3 weeks assignment. And each of these assignments will kind of show you something little bit different. And that will be it. So 2 more assignments. So normally we give around first 2 small assignments, then at least 4 large assignments, and maybe another small one in a normal semester. But this time it's online and the semester is ending a little around a couple of weeks earlier than we normally have. So, but 2 assignments, it will still be there. So around 1.5 weeks more than that left. So I think it will be okay. And it will be in groups. So I think that will be fine. So what we will do today is, so what you have done so far is kind of get a flavor of how to build a network application. Okay, very simple one comparatively, but still how to open socket, do those things and so on. What we'll try to give you in the next assignment is a flavor, just a very small flavor again, of what goes underneath in the network stack. Okay. Now we cannot do that by mucking with the network stack actually. That will mess up your, very difficult, and online is almost not possible with such a large class with no interaction with TAs and all. And it's also kind of messes up your Linux codes and all. So we normally don't do that. What we'll do is we will do something at the user level only, but implement a functionality that actually happens kind of similarly in the TCP stack. And I'll point out why we want to do this. Okay, so we'll do that. So basically the idea is this. So you assume that TCP sockets are not there. Suppose only UDP sockets are there in a mythical world. But you want to do reliable communication. Okay. So TCP gives you reliable in order exactly once. Okay. So we'll not do all that. We'll not try to do in order. We'll not try to do exactly once. We'll study them in theory, how that is done. But we'll do the reliable one. So basically, how can you use UDP sockets to build reliable communication? Which is kind of what happens inside, because TCP works over IP and IP is unreliable. IP does not guarantee that packets will reach the other end. But then TCP has some code in it to ensure reliability while working over the unreliable service provided by IP. So that's what we will try to give you to do. Okay. So what you will do is, as I said, so you had a sock string and sock diagram and so on. So we'll kind of implement, okay, our own socket. So we call it MRP socket. Okay, it's just my reliable protocol socket. Okay, there's no just our name for it. Okay, and you will build a library. So think of that you are writing a C program, same the network application things that you're using, but you will use MRP sockets to do reliable communication. You will not directly use TCP and UDP, so you will have calls on this MRP socket, and you will make those calls only. And is the implementation of those calls will actually use the UDP socket and some other codes and so on. So you will have these following calls: rsocket, rbind, rsend to, rreceive from, and rclose. And the parameters of these calls are exactly the same as the parameters that you have seen for socket bind, send to, receive from, close. So you'll have the same start socket EDR, star socket EDR in, blah, 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 blah. Okay. You see, there is one more value that will come here. We'll talk about. But the number of parameters, type of parameters, all of them will exactly be the same out there. Okay. So you will build a library, a static library using this. And then when you call, write your own C program, just like the program that you have written so far in your assignment. You'll make this rsocket, rbind, rsend to, rreceive from, rclose call rather than making the actual socket bind calls and so on. Okay. So some of these calls are very, okay, we'll come back to this call. So that's what you have to do. And then you have to write an application program actually using this. So all those details are there in the thing. All right. So we want to do reliable communication using UDP sockets. So here is your sender. And here is your receiver. Okay. And you send something. And this can get lost. It's message oriented once again, just like UDP. So it can get, so it's the same as UDP. Only thing will guarantee that if you put something in rsend to, it will eventually go to the other end, which is not guaranteed by the normal send to on a UDP socket. So this is kind of very easy to see. The only way that the sender can know if the packet has been received on the other side is for the receiver to tell it so. Okay. So we'll do something similar to a combination of stop and wait and sliding window kind of things basically. So we will send an ACK. If it gets it, we will send an ACK. If it does not get it, it will not send an ACK. Okay. And then this will wait for some time. And many things can happen. This can get lost, the ACK can get lost, and so on. So if a timeout happens, then it will actually send the thing again. So it has to remember these packets, all the packets that it sent. So it will keep on sending packets. Okay, we'll give you a maximum bound. We'll see the data structures and so on. But then for each packet, it has to remember the packet on the sender side until it gets the ACK back from the receiver. All right, because it may have to retransmit it. And then for each packet, it will have to remember what the timeout is, because all the packets will not be sent at the same time. So if I send something at 103 and my timeout is 0.01, then that timeout should go up at 104 and so on. But we'll see that what happens kind of, sort of. Okay. So basically, you will wait for that, retransmit, wait for that, retransmit, wait for that. When the ACK is received, you forget that message. That's all you are going to do. Okay. So I need, what do I need? Okay. So sender side, I need something to remember which messages have been sent but not ACK. Okay, along with their timeouts and everything. Okay, receiver side, now both will be sender and receiver. So basically, I need it on everything. Okay, I need a buffer to put the received messaging. Okay, because remember, just like you have seen already, the packets can be sent and received at any time. If it is sent, it will come and receive. But then until the user has made a receive from call, the user does not consume. So somewhere it has to be stored. That is what the receive buffer does. Okay, just like I said for the send, it goes to a send buffer, then it gets sent. Okay, the receive also, when it received, it's put in a buffer. And then when the user makes the receive from call, then from the buffer it is given according to TCP or UDP. message wise or byte wise and so on. So we will do message wise here, just like UDP sockets. Okay. So this we need to do. But then just think with me a little bit here. So suppose you made an R. Okay, well, I'll come back to this. Okay. So what we do, so just think of one socket. One socket that the sender will open to send, and the receiver also one socket that will simply open. They can send and receive through both of them, but only one socket per program. That's all you have to do. It will be easy to see how to extend that to multiple sockets, any number of sockets that you can open. But again, that complicates the data structures a little bit. And given the time that you have, if you can do one, you can do multiple things. So we just want you to understand the one socket. So think about your just one message send receive. So I have a sender and I have a receiver. Okay. So the sender side will first make an R socket call, which is going to be exactly the same as earlier. Only thing, you will do a option called sock MRP. This will be interpreted by your library, so it's okay. Just to, you have to give some value. We don't want to give dgram or TCP or something. Otherwise, when you make the R socket call, it does exactly the same thing. It basically will see some more thing, does something, then makes a socket call, okay, with a sock string. So I will implement that with a UDP socket and then returns an ID. And this is the ID that you will return from the R socket. Okay, so its parameters and the return value will be exactly the same. But this will be something we'll see. We'll do some other things. Okay. R bind is straight and simple bind. Okay. Same parameters, makes a bind call on that socket. Okay. And you put this IP address port and so on. You have all these things. Okay. So just like your normal thing, you will create a socket ADR structure. You will put up the values IP address port there. Pass this as parameter here. Okay. And just make the bind call, and whatever the return value of the bind call, you will just blindly return. So implementation of R bind is simple. What about R send to? Parameters first of all is exactly the same. Exactly the same. Return value is exactly the same. Okay. Normally this gets put in a send buffer and then it gets sent by something. Okay. But we'll simplify it. Just make a plain and simple send to call with the same parameters, whatever the return value, return it. So these two calls, R bind and R send to, are straight and simple bind calls, send to calls, and send, return the value. So their behavior is exactly the same as the normal UDP bind and UDP send to that you have seen. Socket is also makes a socket call, but there are something that we will have to do. Okay. We'll see what that is. Now, what about R receive from? Again, parameters and return values are exactly the same. Okay. Now, that will depend on whether something has been received in the receive buffer or not. If it is received, then you should go return that. If it is not received, then you should block. Okay. So I will call if any message in, I will call that thing a received message table. Okay. If any message is there already in received message table, okay, return that message and delete it. So this is just like what normal socket will do. When you make the receive from call, there is underlying receive buffer. Okay. So if any messages come in the between, those are queued up in the receive buffer. It takes the first message, gives you the as a return value of the, not the return value in that parameter that you pass in the receive from call. So it's if any message is there, okay, so you not return that, return first message in the queue, okay, and delete it from the table. What if there is no? Okay. Else you have to wait. Now, this is where implementing inside OS and outside OS matters. You cannot really make it wait indefinitely because then they have to be signaled and so on and so forth. So once you do signal and all, do some more OS, I can point out at the user level how you want to wait, but we don't want to complicate things for this assignment. Okay, so we'll just sleep for some time. Okay, so what is happening here, and this entire thing, delete it from the table, return, else sleep for some time, and then go back to here. You can write a while loop accordingly. So your RReceive from function, which you're calling from your user program, just like the normal programs you've written, okay, it checks this received message table. Okay, if any message is there, it takes the first message, puts them in these appropriate parameters as normal receive from, returns the number of bytes received. Okay, in here, okay. Standard, what happens in a receive from call, you have to check for the buffer size and size of the message and so on and so forth. Otherwise, truncate the message and so on. Normally, what happens in a UDP receive from. Okay, and then you delete that message from the table and you return. So in that case, because you have returned something, your receive from should not block, just like a normal receive from. Else it should block. Now for this assignment, for simplicity, we'll block it by saying something sleep for, let's say, 1 second, and then come back if anything has been received. So note that you as a user have made this RReceive from call from your code, okay, but that function does not return until there is something out here. So even though it is consuming the CPU underneath a little bit, okay, it does not return basically. So to your program, your application program that is making this RReceive from call, it is as if that call is blocked. We're just kind of simulating it with the sleep. We can make it go to sleep and then signal it and so on, but let us not do this now. Okay. So far, so good. And then R close. We do something, 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 and then close the socket. So your sender will make an R socket call, then an R bind call. Okay, I do not say sender. Any code will, when it wants to send, it will make an R send to call. None of this will block. Okay, well, this may block. If send to blocks, then R send to will block also. But these calls are simple. R receive from will do this, and R close will close. So instead of your socket bind send to receive from close, you are using R socket R bind R send to R receive from R close. So far, so good. Are you with me?
Yes, sir.
Okay. What are the things that we have not done?
Inserting message into read message table.
Receive message table. Very good. Okay. I have said if any message in receive message table, but in none of these calls, okay, is there anything to actually receive the message? Okay. But then remember, so two things not done yet. One, who inserts messages in the received message table and handling timeouts and retransmissions. Okay. So who will insert? So you are making this R star calls here. Okay, R socket R in this. This is your Linux OS. Okay, and you have basically UDP sockets. All right, and you have basically out here the standard UDP socket calls. So this is your MRP socket. You've just written a layer of software on it, implementation code. Okay, so now I do not know in this UDP socket when will the message come. So if I have to to receive that message of UDP, I have to somewhere I have to make a receive from call. But then if the user has not make an R receive from call, should I make the receive from call? Okay. First of all, because see the message, this is what you're getting into the OS. Remember, the user can make whatever calls wherever, but messages will keep on coming anyway if the other side has sent it. The user may ask for it for the message later on when it makes the receive from call. So somebody will have to wait or look for messages coming in from the other side basically. But if I use the same thread as the normal user's code thread for this, if nobody is sending, I will get blocked. And if the user wants to send a message, it cannot send a message. Are you with me? So think of this possibility. Okay. I have written an application code. It will first send a message. Okay. But then the other side may also send messages. This is a UDP socket. So first this one will first send some messages, then receive some messages. But the other side has started sending the messages, which will wait for me in the receive. So to receive that other side thing, something in the OS has to wait in this receive from call. But I have only one thread so far, the user application code. Okay. If I make that wait in the receive from call, the application cannot send because if nothing has come so far, it will get blocked out. Are you with me? The problem? Yes, no, please.
Yes, sir.
Okay. So what I will do is I will create another thread R whose sole job is to wait on the receive the message, do something in this OS, quote unquote OS tables that I'm trying to simulate. Okay. So what will R do? Okay. So it will wait on receive from on that socket that you have opened. All right. So it will get blocked if nothing is there. Doesn't matter. My main application thread is different. It's a separate thread that is waiting on it. On receive of message, okay. So there are two possibilities. It is a data message, okay, in which case put it in. So this is the one that is populating that table, receive message table. Or B, it is an ACK message. Okay, then we'll see what to do. But I have got the answer to this first one. So there'll be another thread R. Okay, so you run your a.out, that is one thread of execution. But somewhere in that, we'll see where it is done. Okay, there'll be another thread R, whose sole job will be to wait on the receive from on the UDP socket created. Okay, look at the messages that are received. If it's a data message, put it in the receive message table. If it's an ACK message, do something. We'll see what it does. Okay, so that's the first one. And then the second one, who handles the timeouts and all. So then I create another thread S, because my main thread is the user application. It is doing whatever it wants to do. I should not kind of block it for doing my own OS work, basically. Okay. So basically S does this, sleeps for some time. Okay. Then wakes up periodically. And does the following. 1. We'll see the table. Look up the unacknowledged. I have another table called unacknowledged message table. Okay. Check if any timers. So there was something small wrong that I've said. I'll come back and correct it. Check if any timers have expired. Okay. If yes, retransmit that message, reset the timer. So it just goes through that table. So what is the unacknowledged message? The thing that I have said slightly wrong. It's not just send to, okay, port. So this is the one that is populating this unact message table. Unact message table. Okay. So let's try to understand what happens. So when you make an R send to call, okay, you'll call send to, all right, and then send to return something. Then it basically, so my unacknowledged message table will contain, you have to design this table exactly, okay, some message ID to identify this message, okay, destination IP port to whom it should be sent, because remember this is an UDP socket, so I can use the same UDP socket to send to multiple different places. Okay, message body or a link to the message body. What is the message that I have to send? Okay, and time at which it was last sent. So first time I send it, I put a message ID, I put the IP port to which it is. Okay, I put the content of the message, I get the local time from my clock, the standard C function call for it. Okay, and I just put the time in. So this is what the send to call will do. Put this thing out there first time, and then the send to returns. This kind of it has sent the message, put the relevant information in the OS. Now S when so there will be other entries like this. Okay. Now when S wakes up periodically, he'll look up the table. So there are two possibilities: table is empty, no one acknowledged, it goes back to sleep. Okay. Otherwise, it looks at the current time, again calls that C function to get the local time. Okay. And then it goes to each of the messages and says local time minus this time. Is it greater than the timeout value? There's a fixed timeout value that we are using. That's there in the assignment. So if for any of them, current time minus the time it was last sent is greater than the timeout value, that means it has timed out. This acknowledgement has not come. So it will resend the message to this destination IP port, okay, and then set this time to the current time. So this is the time it was last sent. So send to will populate this table only when it was first sent, and then thread S will keep on changing, periodically waking, checking, and send it, resend it if the timeout has happened. And do that for all the entries. And they'll go back to sleep. Are you with me?
Yes, sir.
Okay. Good. Now, who do you think will remove entries from this table? Because S is only changing the time.
thread.
That R thread.
RR.
This is what this question mark happens. If it is an ACK message, again that message must contain some message ID. So you kind of get a flavor of header design also. Okay. It will look at ACK message, it will look up that message ID. Whichever message ID it is, the ACK has come, it will just remove it from the table. Note that it's a little bit data structure issue out here. We don't expect anything, but you should think about these things. So since it can remove anything in the middle, you can actually get holes in the middle. Maybe the second message, first and third message ACK has not come, but the second message is ACK come. So we'll remove this entry. So when you put in also, it's not as simple as adding to the end of the queue or something. But that's a small issue. I think you know how to handle it from basic algorithms. Okay. So now basically I have these two tables and these two threads. So this is what I have with each socket. I am only using one socket. Actually, you will have, you don't need two tables, but you can put IDs out there. The socket ID also out there to have one table. Another message ID, you can put socket ID to say which sockets table is this and entry is this and so on. You can do it in different ways and you can use the same two threads to do. But we're doing only one socket. In your user program, we expect you to use only one MRP socket at a time. All right. And then you have to create another one. Only once you've created one, closed it, only then you're allowed to use another one. Okay. So somebody will need to create them, initialize them, and so on. Where do you think this will happen? Which of those calls are socket, are bind, are send to, are receive from, are close?
R socket.
It has to be R socket. You don't want to create it a priori. Only if the user wants to create a socket, then you have to associate data structures with the socket, which is exactly what the OS does. So now going back a little, your R socket call is basically create the two tables and in it create S and R, okay, and then you make the socket call. And this return value you return. Okay, R bind is simple, just bind, nothing else. R send to, okay, as we have noted, okay, do a send to. This is the one that you will return. Bind also this is the one that you will return. Okay, populate in ANAC message table. Okay, R receive from. Okay, again the same thing. We have already done this. If check, then do something else. Do something. R close. Okay, free the tables. Kill S and R, and then you call the close socket. Normal close call, and whatever the return value. It's the flow of things proper. So at any point of time when you're using it, there are actually three threads running. The main application thread, which is free to do whatever calls out of these 5 calls or anything else it wants to do. But moment it made an RSocket call, there are 2 other threads that are coming. One's S thread, whose job is to handle the timeout and retransmission, and one R thread, whose job is to receive the messages underneath and put them in the receive buffer. And also handle ACK messages to remove things from the unacknowledged message buffer. Is it clear?
Yes, sir, it's clear.
Okay. So that's what you have to do. You have to implement a static library, okay, which will have these 5 calls, and you will write a small program. Okay, I'll talk about the program a little bit. But for testing it, okay, and again, for this assignment, you will, only one MRP socket. But as I said, just for understanding, I could have added one more field or socket to say, even if you have multiple sockets, which socket's entry is this? Or I could have kept separate tables, an array of tables sort of for each socket for easier search. So there are more algorithmic issues of how fast you can search and so on. But again, we'll keep it very simple. Okay. Okay. So the idea is we'll see how to test this, because there's a problem of testing this. Okay. So the idea for doing this assignment is first of all to show you how something is done underneath, data structures involved and so on. Okay. And the other thing is to when you do the user programming, you have this thing that is all in the user. At the OS level also, and that goes for your OS also. Okay. There are multiple threads that run. It's not that, so when you make a system call, you have already been introduced system call and all these socket bind, etc. system calls, nothing but system calls. Okay. When you make a system call, remember that you don't get a new process or anything. Okay. A system call is just a function. You have been introduced to system calls? Yes, no?
Yes, sir.
Okay. So what's the difference between a system call and just a normal function? What is special about system calls? Okay. You probably will learn it a little later. The system call inside will have some sort of a software interrupt. So you basically change modes. So you go into a kernel mode where you are allowed to do more things basically. So this will become probably clearer to you. Okay. But point is that no new process or thread gets created. It's just a function call. It's just that the process that was running your application code now is running OS code in a special mode. So if I block that thread, that process execution by making a blocking call, okay, then I will block everything. So your OS code also is not just one thread. You have other threads, and then with the threads, now that I have these two tables, note that the received message table is, so if you look at this one, the unacknowledged message table. So S will access that, R will also access that. S will access that for the timeout, R will access that for processing app messages. So what do you think you need? Additional thing that you need based on your OS knowledge so far. Anyone wants to try? This is why I taught you mutex. You need mutual exclusion. Remember, if there is a shared data to which more than one process or at least one process can write, okay, you want to have mutual exclusion. So whenever your S and R are going to access this table, you want to put a mutex lock here and mutex unlock here. You have a critical section because both of them can write to the table. One can try to delete it. Deleting means just setting something to indicate it is free. Depends on the implementation, what you do. Okay. Then the other should not check for it, etc., etc. And these are multiple field things, so it's always that some field changes, the other does not, and so on. So right now, again, when we do mutual exclusion in practice, writing proper code, you try to make your critical sections as small as possible. So that you actually have the highest level of parallelism. So here also the mutex you can actually do, and mutex at the row level basically separate. So somebody can actually access the first row while somebody else can access the fourth row in parallel. So there's nothing common between those. But that again depends on the implementation. In this assignment, we don't expect you to do all that performance thing, but we expect you to access the tables within locks and unlocks so that mutual exclusion is ensured. Why would I want to do for the received message table? Only R handles it, right? So does it require mutual exclusion? The received message table? The S does not access received message table, right?
Yes, sir, it's required.
Why?
Sir, the main thread also accesses
Exactly.
that.
The main thread was making that RDC from call is actually accessible. There are three threads, never forget that. Any two of them accesses, you need to have mutual exclusion. If both of them were only reading, you don't need mutual exclusion. Okay. Now, let's see what you have to do. So creating is, you know how to create threads, how to create R, how to make them start the code that they have to execute. So S will have a routine that will S will start executing, R will have this. Mutual exclusion, you know how to do mutex lock, mutex unlock, and so on. Okay. Only thing is, small, I am sure when you start writing code, you will be able to do this. These tables have to be shared between S and R. Okay. If I did processes, I could have done shared memory. But typically we do threads because it's faster for sharing and all these things. Okay. So if I do this, how do I share the tables? The only way seems to be like declaring them as globals. Or every time I do something, pass a very complicated parameter or something. Okay. But then you don't want to declare it as a global in the program, because if you don't use MRP socket, You can have a program that uses MRP socket as well as plain UDP sockets or something. If we don't use MRP socket, you don't want to create a table. And even though, as I said, we are doing only one MRP socket in this assignment, typically you will want to use more. So how many tables will you create? What should be the structure and so on? Okay. So you don't do that. What you do is you declare a pointer to the proper structure, whatever you define out here. Okay. You declare a pointer to it as global. And then when I said in our socket, you create the tables, you actually malloc memories and so on. But once everybody has the same pointer, then, and in RClose, you got to free the space. I think once you start writing the code, you will figure out how to share the thing. But we don't want you to create the entire table as a global, declare the entire thing as a global variable. So that means that even if you don't have any MRP socket, you have created a table. Okay. And of course, you have to write in rsocket.h. You have to declare, these type tapes and all things have to be there when you use the library. Is it clear? What do we want in the library? Yes, no?
Yes, sir.
Good. So then there's only one small thing to discuss. So how do you test it? Okay. Remember, this transmission will kick in only if something is lost. Okay. But typically, that if you run it in your laptop, both of them in your both server and client in your laptop, or even if you have friends and you run it, the loss will not be too much. You're kind of, you want to test your program as to it will behave correctly during loss, but then you are kind of dependent on the internet to say if it loses or something. It may not lose also. Okay? So what you do is more for testing. You create another small call. The assignment has all details of it in the library that your application can call. Call it a drop message. Okay. You pass it a probability. Say you pass it 0.3. It will create a random number between 0.3 with less than 0.3. It will return 1. So kind of 1 indicates drop the message. 0 indicates don't drop the message. And in your R thread, okay, the first thing, so R, remember, R is waiting on a receive from. Okay. So when it comes here, that means it has come out of the receive from, that means it has received something in the buffer. First thing that you do is you call drop message. It's kind of saying that, so this will be 1 or 0. Should I drop this message? So if 1, don't do anything else. Don't put it in the receive message table or anything. So if it was a data message, it is like, you have not received the data. If it's an app message, it is like the app message is lost. Okay. So put this as part of the library. There is very detailed instruction on what to call and so on. Okay. So you have a very simple application. You have 2 users, 2 programs basically. So there is one string that this one reads and it sends to the other side. Okay. Other side just receives it and prints it. But you send each character in a separate message in a MRP socket, just for testing. And then on the R thread out here, you will call the drop message call. Okay. So some of them will be dropped and so on, and the retransmission will kick in. But eventually, it should print the entire thread string. So if I have sent A, B, C, D, A, okay. Should it print A, B, C, D, A? Can it print anything else if you have implemented your code correctly? So each of these A, B, C, D, A have gone into a separate message. So this is some with IDM1, IDM2, IDM3, and so on and so forth. 5 different messages have gone. So should the other side print ABCDA, or is it possible that you have implemented your code correctly, but it prints something else? What do you think?
Can print something else.
Like?
The order might be changed.
Yes. So the order might be changed. Okay. It can also print duplicate things and so on. Okay. Ideally, in your case, when the drop message happens, it may not happen. Okay. So, but the thing is, it should print A at least twice, B, C, D at least once. So nothing should be missing. Okay. But something else may go also. You know, you have retransmitted, but then the earlier one reaches and so on. The way we are testing, some of those cases are eliminated, but it's okay if it prints something. But at least this one should be printed same number of times. Oh, sorry, at least that many number of times. Okay. So that's your assignment. Let's quickly take a look at that. So right now the deadline, as I said, is 7th March, which is a Monday. So we'll see. So these are all the tables and all. So you get a flavor that there are multiple threads running in the OS underneath to implement the things that you study in theory. You will get a flavor of designing this data structure that the OS uses. You get a flavor of designing the message itself. Okay, so the message sequence number, all these things have to be added. So you need to add a header with each message. You need to decide what is the header. When you pass an acknowledgement, for example, we have seen the acknowledgement will contain the sequence number for a message oriented thing and so on. So the sequence number has to be generated, put along with the message has to be created. So in the last assignment, we told you exactly what to print. Here you will have to design it, which is simple, but still you have to design. And these are the 5 calls, all the table discussion. And threader's behavior is here. Thread SS behavior is here. Everything is stored, mutual exclusion. And I said you can assume that the size is not more than 50. So this is like that window basically. Normally I'm not stopping anything. Moment something is being sent, I'm sending it out to send to. So theoretically it can be anything. There is no window which blocks it if there are so many unacknowledged messages and your unacknowledged message table fills up. But again, we just want to give you a flavor, and this is already a tough semester. So you can assume that not more than 50 messages will be waiting at the received message table without the user having read it, or will be there in the unacknowledged message table without being added. Told you how to test your code. Actually, there is one line I will remove. \0, it doesn't matter. You just send the strings basically. You don't need to send the \0 because you're guaranteed that everything will reach the other end. And when everything has been acked, the sender will close the socket. If the sender closes the socket, then the other side comes out of the receive prompt with a 0. So you know when everything has been sent properly. That means everything has been sent by the sender and the sender has received at least one act for each of those sets. Okay. Small thing that you don't want the including the 0 because there's a problem basically to send the \0. So what is the problem here? So if I send a string ABCDA, okay, \0, and I rely on the \0 on the receiver side to know the end of the string. Is there a problem in this case? The sender sends ABCDA \0 and it for each of those messages it does retransmission if necessary and so on. So all of them will eventually reach the other side.
So the \0 might be received before.
Exactly. Okay. Exactly. So I added yesterday night, but then I realized it. I forgot to take it out basically. So this will be taken because the \0 may come before the last B, for example. Because all I'm doing is reliable. I'm not guaranteeing you in order or anything. Okay. Exactly once, etc., etc. In this case, in order is the one that matters. But you don't need that because the sender, after sending A, B, C, D, A and receiving the ACK for all of them, okay, will close the socket, which means the R thread on the other side, okay, will come out with a 0. Okay. And then if the user makes another receive from call out there, the R thread can inform the receive from, immediately make the receive from come out with a 0. You can just remember that this socket has been closed. Okay. And this is the drop message thing, what to see and so on. So other than your code in this case, because we have asked you to design something a little bit, we want a small documentation from you. So we first of all want to kind of experiment, run your code with these different values of P, that drop probability, and kind of make a table as to what is the number of transmissions that you see, total number of transmissions, average number of transmissions per character, and so on. So it's just running your program again and again with different P values and noting certain, so putting some code to count certain things and then forming a table, and there's a little bit of explanation of your code for that TS to understand. So take a look at that. Okay. And this is a part that, okay, it's not necessary for getting marks, but this timeout is an extremely important parameter. So the drop probability is something we're just using to simulate the drop. Okay, it's not there in the actual network. There's no such function being called. But how do you set the timeout? We'll see when we do TCP. Okay, so the timeout is end to end. Okay, it will depend on what is the speed and so on. That will keep on changing. Sometimes your network is congested, your round trip time will increase. Sometimes your network is free, your round trip time will decrease. The shorter route is present, round trip time will decrease. One link got broken, route changes to longer route, round trip time will increase. So how do you determine this T? Okay. And if you don't do T properly, if the actual round trip time, let's say, is 200 milliseconds, and you set a timeout of 100 milliseconds, then there'll be too many transmissions. You'll clog the network. Whereas if you set it to 400 milliseconds conservatively, then you're unnecessarily waiting when something is lost, even though you could have retransmitted earlier and saved some time. So how to choose T is a very important thing. We'll see some algorithms when we do TCP. But again, we encourage you basically that to change the T. Now, to change the T, you cannot use, sleep is a very large time basically. So if you, normal networks, you set a 1 second timeout, okay, almost everything will come back. But then there's a call in Linux called nanosleep, where you can say so many nanoseconds. So it's similar to time well structure, but then rather than sec and microsec, it's sec and nanosec basically. So when you set very low timeout values, you will see something, things happening out there. So this just if you want to do it, just to see answer in the code. Okay, so that's all I have to say today. And I have nothing more. So if you have any questions, you can ask. Otherwise, we are done. Attendance is a bit poor.